so that we can do our negative control experiments 10,000 times. What do we actually do to get a null distribution? So what we can do is inspect the data that we actually have. So we don't have access to 1 million white mice, but we have access to our 6 white control mice. That's sort of the best we can do right now. And using the sample data, using the shape of the sample data, the histogram of lifespans of these 6 mice, can we make some estimate of what the true population looked like? Probably if we have 6 mice and they all live between 1 and 2 years, it's probably likely that if we got another group of 6 mice, they would probably also live within 1 or 2 years. We probably wouldn't find a 20-year-old mouse. So yeah, you can grab a few of something and get sort of a good sense of what more we're going to look like. This isn't something you can back up deeply with math. This is just how the world works. So how can we proceed with this sort of acknowledgement that future things often look like past things? How do we go from there to building up a null distribution? So one way we can proceed is we can assume something about the shape of the true population. We can say, okay, we have our sample and it looks like this, and that we can fit a mathematical curve to the shape of our sample, and we're going to assume that this mathematical curve is going to be similar to the mathematical curve that describes the lifespans of all possible mice out there in the world. And so if our assumptions are clever, this makes it easy for us to draw new imaginary samples. Say, okay, well now we have the mouse lifespans defined as a mathematical object. Instead of having to go buy more mice and see how long they live, we could just ask this mathematical distribution of mouse lifespans. Well, give me 6 more mice, and I'll look at the lifespans. And now give me 6 more mice, and I'll look at their lifespans. And we could, again, build up this null distribution sort of virtually by dint of having a mathematical model of what mouse lifespans ought to be that's informed by the 6 mice that we actually have in front of us. And so that's if our assumptions are clever, we make it easy to sample from this mathematical model. If our assumptions are really clever, then we don't have to sample. We can just, in closed form, say, I can derive the shape of the distribution of means of 6 mice based on the shape of the distribution of all mice in the world, which I'm assuming that I understand based on the shape of the distribution of my 6 mice. This is very clever math, and it's the fundamental basis of statistics that sort of everyone learns if you take a basic statistics course. These are called parametric statistics. And this is sort of this is the crown jewel of statistics. The fact that this even works is the crown jewel of statistics. There's a theorem that says that these very clever assumptions are basically correct. That in many cases, we can make strong inferences about the shape of a null distribution based on the shape of the data that we have at hand. This is called the central limit theorem. And again, it's sort of one of the basic building blocks of classical statistics. Unfortunately, it's not very intuitive, and I'm not going to teach it because it doesn't really tell you how to think about statistics. And what I want to do is teach you how to think about statistics, how to think about p-values. All right, so that's all based on this assumption that, okay, we've got our 6 mice in front of us. We can describe this with math, and then use the math to prove things about other math. The other thing that we can do is just assume that the 6 mice that we have in front of us represent exactly the distribution of the true population. It's probably not true, but it's as good a guess as we've got. We've got 6 mice out of the possible infinity of mice, and they lived this long, each of them, so that can be our best guess as to what future mice, how future mice might live. Okay, so if that's the case, if we make this sort of slightly crazy assumption that the distribution we have in front of us is exactly the same as the true mythical distribution of all mouse lifespans, then it becomes really easy to rerun this experiment again and again and again. We're going to say, okay, well let me take 6 more mice. randomly from this distribution of all possible mouse lifespans, which happens to be the ones that we have in front of us. And that will be a new random set of 6 mice. And we'll take another random set of 6 mice from these lifespans that we have in front of us, and that'll be a different group of 6 mice. And we can do that again and again and again, in the same way that we could have done it with real groups of 6 mice, but it's much cheaper, because we just do it on a computer. And without having to assume anything about the mathematical shape of the distribution of these 6 mice. We just say, these are the lifespans we observe. We're going to repeatedly resample them and build up a null distribution. So now let's actually work through some examples about this. Because it seems kind of crazy. Like how is this going to work? We just have one set of data. How are you going to fabricate a bunch of sets of data from one set of data? All right, so this procedure then I should mention is known as the bootstrap, this fabrication procedure. And again, it seems impossible, like pulling yourself into your air by yanking on your bootstraps. Or if in Germany, the procedure is known as the Munchausen procedure, because the stories of Baron von Munchausen, he pulled himself out of quicksand by yanking on his hair. So fundamentally, this bootstrap is this sort of making up more data from the data that you have, and somehow that's okay. And the reason that's okay is that the mathematical theory is deep and solid. This guy, Bradley Efron, in the 70s and 80s, really made it clear that this is not just sort of completely made up stuff, but this works, and we'll talk a little bit about why this works. But fundamentally, this is what we call non-parametric statistics. We don't assume that our population can be described in any simple mathematical way. We just assume that the data that we have in front of us are the best description of our population. So let me give you a quick example of the strengths and weaknesses of parametric versus non-parametric statistics. So I'm going to use a simple example of fitting some x equals y function, or some y as a function of x. Okay, so let's assume that we're going to be fitting a line. This is a parametric exercise then, because we know that a line has an equation y equals ax plus b. So really the world is characterized by these parameters, these a and b. And so if we have just a few data points, we can still fit a pretty good line, because we're assuming that these are coming from a line that's been corrupted by some sort of measurement error. And so because we're making this parametric assumption, we can fit a really good line with very few data points. The problem with parametric statistics is when your assumption is wrong. What if we have a lot of data points? And we make the same parametric assumption that it's a line. And we fit a line, and we get a really crummy fit. So the strength of the parametric approach is that if you guess right, you really don't need very much data to get a good sense of what's going on. But if you guess wrong, you're your host. So the non-parametric approach to the same problem would be to say, okay, I'm not going to assume that it's a line. I can't assume very much. Number these. I'm not going to assume it's a line. The best thing I can assume is, maybe it's something like that. And obviously, if it really was a line, you know, this is a much worse model. It doesn't generalize well. It's corrupted. It's totally corrupted by noise. You know, if you're really looking at a linear dose-response relationship, this is the better thing to do. On the other hand, if it wasn't really aligned, you just say, okay, I'll let the data be my guide as to what the shape of this functional form is, and you have enough data, you can get a really nice model without having to specify in advance, oh, I think it's going to have this particular shape characterized by this particular mathematical structure. And so that's the strength of non-parametric statistics as well. We don't have to assume anything about the shape of our data. We can just ask questions of it. We can ask, well, what is, you know, in this case we can ask, well, what is f of 3.5, even if we don't have a data point right at 3.5, and without having to assume that it falls into this form. So how does this work with the bootstrap? Probably all seems a little obscure and abstruse, but I promise we're going to get to specific examples, especially in homework. All right. So I'm going to start with sort of a simple case. And we just say, okay, again, we have some number of mice, and they're control mice, and we want to know how much would we expect the mean lifespan, or the mean weight, or whatever, the mean of some value, some number that you would calculate from your mice. How much would we expect that mean to vary upon repeated sampling? And remember, this is an important quantity because that's how we build our null distribution and ask what the p-value of having a mean bigger or smaller than what we see in the control population. All right. So let's say we do our negative control once. And we get this distribution of observations. We're going to do 11 mice, and I don't know, you can't have a mouse that weighs 0. Maybe they score 0 on some test of mouse fear. This seems like a plausible thing that mice might score 0 on. So you get one mouse that scores 0, 3 that score 1, Right, so this is our control data. This is what we have. And so the mean of this is 3.12. So here's the mean. And we want to know, all right, what if we did this experiment again? Where would the mean be? What if we did this experiment 10,000 times? Where would the mean typically fall? And again, as I've been belaboring, we could get 10,000 more sets of 11 mice and do the experiment over again. Or we could assume something about the shape of this distribution and mathematically do it. But this distribution, this looks a little weirdly shaped. It's got sort of 2 humps. Maybe we don't want to assume anything about the math. Maybe we're just going to assume, again, that this distribution really looks a whole lot like any possible future sample that we could get out of mice in the world. So how would we simulate future samples of it? Well, we would just pick 11 more mice at random from this distribution. Now here's the trick. We don't want to pick 11 mice without replacement because then we're always going to get the same 11 mice. We want to pick random numbers 0 through 10, the index of the mice. And it's okay if we get 0 repeated, because again, if the sort of truth of all infinite mice out there were shaped like this, it would be totally possible to get a population where you had 2 mice that had 0 fear score. So that make sense? Everyone feel okay about the fact that we're gonna sample from our mice with replacement? All right, so what does that mean? I'm gonna just make some random numbers. In fact, I made real random numbers on a computer. And so remember, these are our 11 mice. They each have a little number on their little ear tag. You know, mouse 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, we counted to 10. All right, so I'm going to draw some random numbers. I'm going to draw 11 random numbers in the range of 0 to 10. And so when I did that, so these are 11 random numbers that I got from the Python random function. All right, so let's use those to come up with an imaginary replicate. All right, so let's see, mouse. All right, so the first one, we have two of mouse 5. So mouse 5 is there. So 2 of mouse 5. Does that make sense? 1 of mouse 10. 1 of mouse 8. 1 of mouse 9. Oh, another mouse 5. Mouse 1. Mouse 8 again. Mouse 7. Mouse 1. Popular mouse 1. And mouse 4. Okay. So this looks credible. Well, you know, it's not the same as this, but it's not that different. This is what you would expect. If the true distribution of mice fear scores looked like this, then this is a totally reasonable distribution that you might get by chance alone, just randomly by getting some different mice. And it has a mean of almost 4. All right, and then we can do this again. And I'm not going to belabor the point of doing it again. But you can trust me that these dots I'm going to draw are also generated from exactly the same procedure. I just got new random numbers, and I got this distribution. And it has a mean of somewhere around here. So you can imagine doing this again and again and again and asking, where do these means fall? Can we make a histogram of the means of this control population on repeated resampling? So everyone, I think, should be getting, okay, where are we going with this? All right, so we're going to repeat this many, many times. And right, so you know, here is where the mean of our population was, and then we resampled it once, and we got something that was a little bigger, once, and we got something that was a little smaller, so you know, we can build a histogram, and I don't like drawing histograms because I'm lazy. And so eventually, we're going to get a distribution of values for where this resampled mean is going to fall. And then we could, if we knew that, for example, some other group of mice had a mean fear score of 7, we could say, well, how likely is a mean fear score of 7 to happen due to chance alone? And that would give us a p-value. Everyone feel comfortable with this line of reasoning? So there's one important caveat. So if we repeatedly sampled from real mice over and over again, got 11 real mice, we calculated the mean, and we got another 11 real mice and calculated that mean, eventually we would be able to draw a distribution of these means. And the center of this distribution would probably be pretty close to the sort of true population mean. This repeated resampling isn't going to get us any closer to the true population mean. The center of this distribution is basically going to be the mean that we observed here. So we're not learning anything deeper or newer about the truth. What we're learning about is the relationship of sample means to the parent distribution, the thing we're sampling from. So it tells us, again, it tells us sort of this spread around the mean, which is all that we need to make a p-value. And we'll talk about this in a couple more minutes in more detail. All right. So how should we characterize this distribution of sort of plausible means? We know that it's likely to be centered on the sample, on the original mean that we observed. So if you know the mean, what's the next thing that we do to characterize a group of numbers? Dig deep, back to lecture 1. Standard deviation. All right. So we can characterize the standard deviation of this distribution. Now remember, that's different than the standard deviation of this distribution. This is the standard deviation of fear scores. This is the standard deviation of mean fear scores for a group of 11 mice. Does everyone see that sort of conceptual distinction? This conceptual distinction is so important. This standard deviation is called the standard error. So the standard error of the mean is nothing more than the standard distribution, the standard deviation of the distribution of where the mean might fall upon repeated trials. So that brings me to a point about error bars that I think is a really important point to make. What error bars do you plot? And when you see error bars plotted one way or another, what does it mean? By the way, we're not going to take a break today because there's a lot of content and you probably want to learn statistics because you're taking a statistics course, so my apologies. All right, so you can make a bar graph two different ways. So these are two means, blueberry mice and control mice, or what have you. Sorry, I'm picking on these poor blueberry mice. They didn't do anything wrong. Okay, so we could plot the mean of these two different groups plus or minus the standard deviation. So what is this plot telling you? Well, first, not much. If you remember from my first lecture, really I'd much prefer the dot plot of seeing all the mice. But if you're going to plot the mean plus or minus the standard deviation, what is it telling you? It's telling you that most of the mice live in this region, and that there's some of the mice live out of that region. If we make some assumptions that mice fear scores or lifespans are normally distributed, we can say, well, 66% of the mice live within this region, and 95% live in twice that region. So the mean plus or minus the standard deviation tells you where the population is. What about the mean plus or minus the standard error? What does that tell you? What lives inside these bars?
What's the difference between the sample and the population?
Right. So what lives between these bars is where the mean might be if you sampled it again, or many times. So these tell you most of the time this line, this mean, is going to be right around here. most of the time. These tell you most of the time a random mouse is going to be somewhere in here. So this tells you something about the population. This tells you something about the mean, and where the mean is likely to be. Mean plus or minus the standard error. A lot of times people choose this because it's smaller. That's not really a good reason. A lot of times people don't tell you where the error bar means. If you see that, assume they're incompetent and don't trust anything else in their paper. Fundamentally, it's a matter of choice. Personally, I like to plot the standard deviation for the same reason I would much prefer just to plot the darn dots in the first place, to show you what the population looks like and let you draw your own conclusions. Here, this plot is already making a lot of assumptions for you. It's assuming, well, under what procedure is this repeated resampling going to happen that generates these tiny bars? Is it this parametric assumption? Is it the bootstrap assumption? Is it any number of different ways that we can get these? This is closer to the raw data, so I like that better. But you really want to understand what these error bars are saying. These error bars are telling you about where the mean might fall. These error bars are telling you where a random animal from the population might fall. Okay. All right, so mean and variance. That's one way we can characterize this distribution of plausible means. There's actually a better way to describe where the mean is likely to be. And many of you have probably heard about these, but these are unfortunately not taught as commonly or as carefully in most basic statistics courses. We're talking about confidence intervals. So here we have this distribution of where the mean plausibly might be. And we can construct a region of this distribution that contains 95% of all the plausible places that the mean might be under repeated resampling. And so what do we say? We say, "95% of the resampled means live between these two bounds." So you could imagine, how you would do this with a histogram. You'd sort of go up, you count up here until you hit 2.5% cumulative area, and you count down from here until you hit 2.5, and then the rest is 95%. And again, in the homework, you'll have ample opportunity to actually see how you do this in Python. Okay, so this is interesting, but what's really phenomenally striking is that if you construct an interval in this fashion, then that means that 95% of the time, an interval constructed that way will contain the true population mean. But let me write that down and then we'll unpack that a little bit. So this is crazy. Here we're talking about the distribution of resampled means compared to the mean of our original sample. So these red arrows compared to the mean of the blue arrow, to the blue arrow. That's what this distribution is. And then what I'm asserting is that if you follow this procedure, 95% of the time you will get an interval that contains not the red arrows, not the blue arrow, but this sort of mythological true mean that we would converge to if we actually had infinite mice and got to keep repeatedly grabbing 11 more mice and making them afraid. This is crazy. And this is fundamentally the sort of very deep math that makes the bootstrap work. And there's assumptions to it. And the bootstrap is not a panacea. Many times these assumptions are incorrect. And again, in the homework, we'll explore how that fails. But basically, the intuition boils down to this. It's called the bootstrap analogy principle. So we've got some platonic truth that's out there. So the X files way. The truth is out there. And there is a true mean. And we can draw samples. We can get ourselves 11 more mice and see where our 11 mice scores fall. I don't even know if that's 11, it's okay. And these mice will have a mean. The sample will have a mean. And so any given sample will have a mean that's some distance from this true mean. And so if we got lots of samples, and we knew the true mean, we could sort of build a distribution for how far our sample's mean is away from this platonic truth. Did you buy this, that there is such a thing as a platonic truth, and that we might be able to get access to it by doing repeated replicates? If you don't, you probably shouldn't be a biologist. Investment banking might be better. Okay. So then let's do our sample again. And it has its mean. And then if we resample from our sample, we'll get some other resample. And it'll have its own mean. And these two means will have some sort of relationship between them. And now this we can do. We can resample a whole bunch and calculate where this mean falls, and thus sort of implicitly calculate this distance. And that was just this distribution of plausible means. So the whole bootstrap hinges on the fact that provably this relationship is congruous to this relationship. This sort of unknown and interesting quantity about how far our mean might fall from the true mean can be simulated and interrogated by looking at how far a resampled mean falls from our original sample. And that all comes because we assume that this thing looks enough like this thing that this procedure is the same as that procedure. Does everyone kind of buy this? So that's what allows us to say interesting and deep things like, if 95% of the resampled means live here, then if we construct this a whole bunch of different times, 95% of such intervals will contain the true mean. That's how we can go from a statement about the resampled mean to a statement about where the true mean might live. Any questions about that? All right. So let's do a quick example. Let's look at a different kind of study, even more clinical than this blueberry stuff. Let's look at a weight loss trial. So we've got some number of before and after weights for participants. You know, you weigh in at the start of the trial and you weigh out at the end of the trial, and then the number of interest is how many pounds you gained or lost. So let's try to figure out what the confidence interval around the average amount of weight gained or lost would be. All right. So again, we have some histogram of weights that people have gained or lost. And again, I'm lazy and I'm not going to draw it as a histogram. It's going to look like that. And let's say that it's basically centered on -5 kilos, or pounds if you prefer. So this is going to be our distribution of lost weight. It has a mean of -5. And we want to know, well, how likely, you know, let's put a confidence interval around this to tell us about how likely is it that if we did this a bunch of times that the true mean would fall in there. And note that I'm not saying how likely is it that the true mean is in this interval, because the true mean isn't some random thing that might change that has a probability of being here or it might be here. It's one thing. So the only thing we can talk about is how likely is our procedure to capture the mean. It's a subtle distinction and it doesn't actually matter too much. All right, so we can do our resampling trick. Look at the distribution of means. And in the homework, we're going to see that sort of invariably this is narrower than that. And that's interesting and useful. And so it's still going to be centered basically at -5. And for convenience, let's say that 95% of the plausible means fall within -6 to -4. So that says, okay, the 95% confidence interval is from -6 to -4. Importantly, what does this confidence interval not include? What do we want to show our weight loss regime is better than? If you're going to be on a diet, you want the diet to be better than what? Better than nothing. So we want to show that our confidence interval does not include 0. But the mean, that the true mean, that we are unlikely to, it's hard to say this right because the true mean doesn't have a probability, again, as I mentioned. We are unlikely to have accidentally built a confidence interval that does not contain the true mean, and the confidence interval does not contain 0. Ergo, 0 is probably not the true mean. That's sort of the closest to correct that I can say it. But sort of colloquially, we can say the confidence interval does not contain 0. Therefore, we think the effect is likely to be here. And so, this isn't a p-value, but it's a hypothesis test. We're saying, okay, we kind of reject the possibility of no effect because we see this effect. And so there's a really deep duality between confidence intervals and p-values. And I think you see that duality best when you work through the case with the bootstrap rather than sort of drawing math on the board. So that's one of the reasons I'm teaching it this way. Because I think confidence intervals are really important and really underutilized and actually solve a lot of the problems with p-values that I discussed earlier. Okay, but nevertheless, what is that duality? How do we get a p-value from this? I think I can do this before class ends. All right. this distribution? What sort of probabilities are we reading out from this? We're basically getting what's the probability distribution of observing a mean from some random sample of 11, or of 11 mice or of our weight loss patients. What's the probability of observing a mean of that sample of any given value, given that the true mean, the thing that we're sampling from, has a true mean of 5 kilograms lost? So that means that we can read out well, what's the probability of an observation bigger than or equal to 0, given that the true mean was -5? So if this distribution went all the way out here, we could ask what the area under here is. And that would kind of give us, that would give us a value that's a probability. But does it give us the p-value? Is this the p-value that we're looking for? What's the p-value that we're looking for? What's the null hypothesis?
That's true equals 0.
Right, so we want p of something given. So what do we want to know about the probability? What's our actual observed data? We actually observed a 5 kilogram weight loss. So we want probability that our observation is less than or equal to -5. And I can put the absolute values, so we're doing the two-tailed thing. But to be less fussy, let's look at it like this. So this is the value that we want for our p-value, right? This is what we can calculate from the confidence interval. Now what I assert is that these probabilities are identical. Why? So fundamentally, this question is, if this is the true population, if this is what sample means are truly look like, where they might fall, how likely is something to show up out here, right? That's what this thing is asking. This thing is asking, under the null hypothesis, how likely is something to show up out here? So these kind of look symmetric, right? So remember, the bootstrap analogy principle is all about the shape of the... Tell me I kept it. No, I erased it. So the bootstrap analogy principle is all about the shape of the distribution of differences. Those little red arrows between the true mean and the sampled mean, or between our sampled mean and our resampled mean. So really we're asking a question about the relative shape of this around whatever this number might be. So that means that we can totally get away with just shifting this over to 0 and saying, I assert that the null hypothesis is true. Because remember, that's sort of what we're doing. We say, if we imagine that the null hypothesis was true in some world where it may or may not, in the real world it may or may not be true, we're going to imagine that the null hypothesis is true and ask, in this fantasy world, how likely is it to see what we actually saw? So how do we make a fantasy world in which the null hypothesis is true? Well, the easiest way to do that is to say, well, my null hypothesis is that we didn't lose any weight. So I'm just going to take my actual data, and I'm going to add 5 to everything. And now we get a data set that looks very much like our data set, has the same structure as our data set, but is the data if the null hypothesis were true. In this fantasy world where the null hypothesis is true, where we just added 5 to everything. And then we could repeatedly resample that and get this distribution, which is just this distribution with 5 added to it. So that's how we can go from a confidence interval, which tells us something about where we're likely to bracket the true mean, to a p-value, which tells us how likely is what we observe going to be due to chance alone under this alternative model. All right. So I just want to conclude, and I think I'm going to try to steal a couple minutes from Mike next week to finish up a couple minor points about statistics and hypothesis testing and wrap up some of the homework. But I'd like to finish now with just one little point to try to tie together confidence intervals and p-values. Hopefully you see that there is this duality between them, that both of them can be used to answer kind of a hypothesis test. Is what I observe likely to be due to random chance, which is the p-value? Is the true mean likely to be